Okay. Now we should understand why category the category of sheaves is an elementary topos. And I recall the definition of this object. Definition. Elementary topos. No, I say what we what should we prove for that? Our aim is to prove that the category of sheaves is an elementary topos. For do this, we should prove that sheaves has all finite limits and colimits. The second sheaves, the category of sheaves, has exponentials. And the last point, sheaves has a subobject classifier. Okay, and first of all, we will prove that we have a exponential object, but I should recall what is a exponential in the category exponential. Let P and Q are functors. Two functors, more precisely, the presheaves on C. And by definition, for the exponential object, we should have the following isomorphism. Exponential object is such a functor such that we have the following isomorphism, and we for all functor R, and in particular for representable functor. In particular, if we take R equals y of C, that is home over C to C. C is the object of the category C. Then we must have that the following isomorphism by unit lemma. Okay, and this is by unit lemma. And by definition, we have that this is the same as this home. And thus we have that QP of C is just a home of press sheaves on C from the product to Q. Okay. And proposition which tells us that if F is a sheaf and P a press sheaf of sets on X, then the press sheaf exponential Fp is a sheaf. Okay, let's prove this proposition. Let F and P are press sheaves on sets. Then we know that exponential Fp
You're muted.
Oh, so sorry. Sorry. Okay, we have the following isomorphism for all open U. And y of u is a what is a y of u? Y of u of v is a one element set if v is a subset of u, and the empty set otherwise. Okay. In other words, we have that Fp of u is isomorphic to home from P restricted to U to F restricted to U. And Fp is a functor. Is a functor that is for an inclusion V into U. Each natural transformation alpha can be restricted restricts to V. And thus FP is a that press sheaf whose values on each open U are just the maps of press sheaves. And also it is actually sheaf if I have a current U and natural transformations tau I, then we can collate these maps we can collate this tau I to tau from PU to FU by collating their values. But values are collectible as they lie in the sheaf F. Okay. In particular, now we have proved the proposition, and in particular, we obtain that when F and P are sheaves, then FP, this exponential object, is a sheaf also. And definition, this exponential object FP is called internal home. Okay, or sheaf valued home, or sheaf of germs, or sheaf of germs of morphisms from P to F. Okay. Now we've completed one of the steps, and now I want to discuss the problem of classifying objects, and we start with a particular press sheaf on X. Particular press sheaf omega on X. Omega is a functor such that omega U is a set of all W open subsets of U. And omega of the inclusion is the map, the following map. Such that W maps to W intersects with V. And omega is a press sheaf. And I should recall what is a subobject classifier. Subobject classifier. Definition. In a category C with finite limits, a subobject classifier is a mnemonic map. Is a mnemonic map which is denoted by true from 1 to omega, where omega is a object of truth value. And such that to every mnemonic in categorical sense, mnemonic S to X in C there is a unique arrow phi. And I recall what is a mnemonic. The map H from X to Y is called mnemonic if there is a following pullback diagram. Okay, and there is a unique phi. And example. In the category of sets, let S be the subset of the set X, and we define the indicator such function which equals 0 or true if X belongs to S, or equals 1 if X doesn't belong to S. And we have the following diagram. And here we see that phi S is just an indicator, and with such a phi s, this diagram computes, and it is also this diagram computes. Okay, and phi s is a characteristic function. Okay.
This diagram not only commutes, but it is also a Cartesian square.
Yes, it is a Cartesian square. Yes. Okay. Yes. Thank you. And another example. If G is a Lie group, then we can classify all of G bundles over X. And there is a universal G bundle, EG2 PG, is an object classifier in the category in the over category top over X. Any G bundle over X can be obtained by pullback of this classifier bundle, and we have the following pullback. And also the map EG to BG is monic, as we have the following diagram. Okay, and we now formulate the theorem for any topological space X. The press sheaf omega is a sheaf, and also omega is a subobject classifier for sheaves on X. First of all, prove the first statement. Consider covering of U and if for this inclusion we have that there is a unique V such that we can take such a V is just a union over VI, and then we will have that the intersection is the same as a VI for all I, and we then verify the equalizer condition in the definition of sheaf. Okay, prove the second statement. Consider subobject of sheaf. We now we want to understand why omega is a subobject classifier for the category of sheaves, and consider subobject S of a sheaf. Then S is a subsheaf of F, and SS is a subsheaf. And then for characteristic natural transformation phi from F to omega, we define the following function: phi u for each open u, x maps to the w, which is a union of all double I, where double I is a subset of u, such that x restricted to double w I belongs to S wi. But S is a sheaf, subsheaf, sorry, the subsheaf, and hence we obtain that X restricted to W belongs to SW, and also phi u is a natural in U is natural, and consider the pullback of true along this map. We have the following diagrams. We have a map phi from F to omega. We have this map and one. What is a one? The map true since each point of one one is a one point set. No. We sense each point of one to the maximum element u. What is a one? What is a one?
One is a sheaf which is valued, which has singleton set for each open subset of X.
Okay, thank you. One is such a trivial sheaf. Okay, and we send each point of one to the maximum element u to u from omega u, and we can form the pullback. We can form the pullback, and for each u we have the following pullback. This is a phi u. Phi u was constructed above, and we take the pullback pointwise. That is pu is the subset of fu consisting of this x from pu with the property that phi u of x equals u, and it is the same the fact that p is s p is just s is a given subsheaf. Okay, and it can be verified the uniqueness property. We will skip this. Okay. And now we want to prove the following proposition, which tells us that the category of sheaves has all small colimits. It is an important fact for our aim proposition. Sheaves has all small colimits. Proof. It's an easy fact because we have the sheafification factor. Oh, so sorry. Just a minute. we have the sheavification functor gamma lambda from pre-sheaves to the category of sheaves, and we can denote this as a L, and L is left adjoint to the inclusion factor, to the inclusion factor I. And hence L must preserve colimits. And the second point, if F is a sheaf, then LF isomorphic to F we proved this statement in the previous seminars, and form a coproduct of F and G as a form coproduct of F and G is a pointwise disjoint union as pre-sheaves for F and G are pre-sheaves. Then it implies that it yields a sheaf L of L is our functor, and we take this functor and consider the following. And we know that F is isomorphic to LF, and G is isomorphic to LG, and we can construct the following diagram. Okay. And thus we have obtained that the disjoint union of any two pre-sheaves is a of sheaves. Sorry, of sheaves is also a sheaf. Is also a sheaf. Okay.
Can you explain this last bit once more? Why is it a sheaf?
We know that L must preserve colimits. Then L of F disjoint union with G is the same as a this one. Mhm. In some sense, and mhm.
Okay, now I see. So just LF is equal to F and LG is equal to G. And
Yes,
then
yes.
it follows. Okay, thank you.
I think so. And the case of equalizers and other colimits are treated similar. And the theorem, the central fact, the category of sheaves is an elementary topos. And from these propositions, it follows immediately. We have constructed the subobject classifier for this category. For this category, we have proved that there exists colimits and there exists limits also, and there is an exponential object. Okay, and now I'd like to discuss the last topic of my talk. It is an inverse image sheaf. It's a natural object in this setting. We know that there is a for a map x to y, there is a functorial map f with a star, which sends the sheaf on x. F is a sheaf on x, which sends to the sheaf on y. And by definition, it is the following sheaf for all open V. And also there is a functor in the other direction. Inverse image, which acts on bundles over y and sends it to the bundles over x. And by definition, we just take a pullback. If we have a bundle over x, over y, sorry, over y, then we can form a pullback and of course we have a following diagram. Okay, and the easy lemma if F is a continuous map and P is an étal cover, is a étal over Y, then the pullback is étal over X. It's very easy, and but we will prove it. We know that the pullback is the following set of such pairs consist of X and E, that X belongs to X, E belongs to E, and F of X. Okay, P is étal, and hence there is a open neighborhood of E in E capital, such that we have the homeomorphism then we can consider the following Cartesian product, and it is an open neighborhood of the point X E in the product of X and E, and the map maps this open neighborhood. Sorry. Homeomorphically onto this map, this set in X, and thus this space is étal. Okay. I draw the picture. We have a following diagram. We have the following open sets. Okay, and now we can notice that for each F, we have a functor. For okay, we have a functor, and we can define this functor by means of an equivalent between the category of sheaves and the category of étal spaces, étal bundles, and it's quite easy. We have this category, and by means of lambda, we map into étal over Y, and then we apply F star. Now we in in the following category, and then we apply the factor gamma. I recall that lambda gives germs, and gamma gives sections. Okay, and the composition is this map. And we can formulate the following theorem. We have there is the adjunction. And that is F with up star is a left adjoint to the direct image functor F sub star. And I think that I skip the proof, and I think that I should stop my talk and this is a last point of my talk. Have you any questions?